very much for that very generous introduction. And I am extremely delighted to be, even though it is virtual, to be in the company of colleagues from AMU. There's a very special connection I have with AMU. I mean, I wish I could have been in the campus. It's a pleasure to be there. Thanks also to Dr. Furkan for the opportunity. In fact, most of the things that I'm going to show are actually done by him. So it will be a little embarrassing for me to tell him what I think or my interpretation of his work. So I hope if I make an error, he will forgive me. Uh, okay, I'll start sharing the. Okay. So the title is essentially about fluid structure interactions, and most of the time people think of structural analysis as simply some kind of an add-on. But what I wanted to show here or impress is that actually vibrations can modify the flow so much that one would have to really look at a coupled fluid structure interaction. So there's a number of people who have worked on these over a large number of years. So Dr. Furkan is one of them. Tulsi is working on them, and there are some other people whom if I had to name, we would fill up a lot of space on this screen. This is a picture of our library, Central Library, one of the iconic buildings of IIT Kanpur. And this used to be a pond where you used to have evaporative cooling. Now, of course, that space has been reclaimed, and I hear a garden has come up. So hopefully next time when I present this picture, there would be some other stuff on this. But I like this picture because it kind of tells us that there's a building and then there's a reflection. And maybe once in a while, it's good to just step back and reflect on what has been done. So here are some more virtual pictures from IIT Kanpur, some of our very nice buildings, and of course, a lot of birds. Okay, so fluid induced vibrations are, their importance is well known to most of us, but just to show you, usually we give examples of disasters. It's very unfortunate that we have to resort to this, but that's what draws attention. So the picture on the left is a ferry bridge power station where the cooling towers, they had a breakdown. And what is startling here is that there are three of them which broke down, the others are intact. So clearly the wake effects are important. Okay. So in this kind of a configuration, air could come from any direction. And the lesson learned is that you should not only test the standalone structures, but also the interference effects are very important. So that's very important. The next one is the Tacoma's Narrows Bridge, which had this galloping response, and you can in fact see a small car also on the bridge. Fortunately, there were no casualties. But this is one problem which drew everybody's attention, that how can flow-induced vibrations be really so important. So just to get going, shown here is a canonical picture of a flow past a circular cylinder. So the top image is a steady flow, the one below it is vortex shedding, and then how the vortex shedding induces vibrations, and then the vibrations can actually modify the flow in terms of a stronger vortex shedding or change in the frequency and so on. So we'll start with a very simple system to begin with. This is a single degree of freedom system, and the dynamics is very simple. It's a harmonic oscillator, except that the right hand side is coming from the fluid. So you could have vortex shedding, and that leads to alternate forces. That's encapsulated in the lift coefficient.
Sorry to interrupt you, sir. I think there is some problem. Your slide is not changing, and it is not in full screen mode as well. Now it has changed.
Okay, so okay, so
It is
what?
also not in presentation mode.
Okay. So now it is not in presentation mode because I changed it. So let me see.
Okay.
Let me just try it. Okay.
Okay.
How about now? Is it changing?
No.
Okay, okay, okay. That's good. At least we know it's not changing. Uh, so maybe what I do is I unshare, and maybe I probably should share my screen instead of sharing just the slide. Let me see if that will work. Okay, I say my entire screen. Okay, I say share. Okay, and now you are able to see my screen, right? And with the slides on it? No.
No.
Okay. Okay, how about now?
Yes, sir.
Okay, great. So now I will start from the first slide. So now it's in full screen mode.
Yes, sir.
Okay, and it is changing.
Yes, sir.
Okay,
Fine,
so
sir.
yeah, thank you for being so patient and also letting me know.
No, sir. I mean, we are sorry for these small glitches.
No, 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 no. Actually, I'm not so familiar with Google Meet, so I apologize. With Zoom, I am a little bit more familiar. So I'm glad it's sorted out. So again, these are some pictures. I'll quickly go through them. And these are the Ferry Bridge power station pictures that I was talking about, and the Tacoma Narrows Bridge. So I hope you remember my commentary. I'll just move on. And these are the animations for very simple animations for the vortex shedding and something that leads to vortex-induced vibrations and the modification of the flow. Okay, so now we are on a slide which is titled Vortex-induced vibration with a picture of a cylinder with springs and dashpot. Can you confirm, Furkan, if that's what we are
Yes,
on?
sir.
Okay,
Yes, sir.
perfect, great. So, so as I was saying that here the right hand side is coming from the fluid forces acting on this little cylinder, which has a mass ms, and we typically non-dimensionalize it to give us a mass ratio m star, which is essentially the mass of the body divided by the mass of the fluid that it displaces. And then in terms of the frequencies, I mean, there's a natural frequency, which we also non-dimensionalize. So f, small f ns is the natural frequency of the system. And d is the diameter of the cylinder. U is the incoming flow speed. And if you invert it, that's the term which is very common in fluid structure interaction. It's called the reduced speed. Okay, so clearly we are using the speed and the natural frequency to give us a non-dimensional speed. And then, of course, the force coefficients, the vortex shedding frequency, the Struhal number, and the frequency ratio of the vibration and the natural frequency. So these are things that we are going to, this terminology we are going to use quite a bit. Okay, so the whole idea is that there is a flow coming in from left to right, and there could be vortex shedding on this circular cylinder, and there's an unsteady flow. And if the vortex shedding frequency matches the natural frequency, then you expect something close to a resonance, what you see in linear systems. But the interesting part is what happens if the two are not exactly the same. That means the natural frequency ns and the vortex shedding frequency, they are not same, but they are close to each other. And that's where magic happens, and that's what I wanted to highlight here. So here is a picture of the frequency with speed. So this is a dimensional plot. So f is the dimensional frequency, u is the dimensional speed. So typically what happens if you do these experiments in a wind tunnel, the vortex shedding frequency would linearly increase with the flow speed, such that the Struhal number would be constant. Okay, so if you did fv0 times d divided by u, that would be a constant over the entire speed. But the frequency itself increases linearly. The natural frequency is, of course, constant. That does not depend on the speed. So there would be one point where you expect resonance. So classically, if we were to think of this linear spring mass system coupled with a fluid system, then we would expect large amplitude oscillations at a certain frequency, and then smaller velocities and larger velocities, we would expect very small vibration amplitude. Unfortunately, that's not what happens. So what happens in reality is what is shown in this picture. So for a range of speeds, it turns out that the vortex shedding frequency of a vibrating body changes to the natural frequency. So therefore you get this black line where the vortex shedding frequency locks in close to the natural frequency. And then it kind of jumps back to the original shedding frequency as if there was no structural interference. So this is a very interesting phenomenon, and one could ask a lot of questions. Okay, question number one is, do these frequencies exactly match? Question two could be, what is the range of this lock-in? For example, does it depend on the mass ratio? So if I take a lighter system versus a heavier system, do I get a bigger range of lock-in? What about the Reynolds number? Okay, what about the amplitude of the system? Does it change during the lock-in? Because this is a jump, so do we get a hysteretic behavior? Okay, that means multiple solutions at a given speed. What happens if I have multiple degrees of freedom? This is a very simple system. So if I had maybe 2 or 3 degrees of freedom, or I replace this system with a beam, then what would be the scenario? So we are going to look at some of these questions. Hopefully, some exciting things will come out as we go on. So this is the first system that I would like to show you, which is a very simple laminar flow. The Reynolds number is 100, so there's hardly anything going on in the flow, anything different from a stationary body. So the whole thing is mounted on a spring on an elastic support, and you let it vibrate. So the x-axis is u star, which is essentially the reduced speed, and the y-axis is the non-dimensional amplitude of the vibration. So you have seen that AC is the amplitude of the cylinder vibration, and it is non-dimensionalized with the diameter of cylinder. The mass ratio is 10. So there are some branches that have been marked here. So first there is desynchronization. Desynchronization means the fluid flow doesn't really care so much about what is happening structurally. So vortex shedding frequency is very similar to what you would see for a stationary cylinder. So there is desynchronization regime 1 and 2 on either sides of lock-in. And then here is a U star range where something interesting happens. So first the cylinder goes through some vibration, and it gives some kind of a beating phenomena. So it goes through this structure where you get a frequency, a high amplitude frequency, but that is on an envelope of a very low frequency. So that's why you get these beats. I have not shown the time histories, but you can take my word for it. And then at a very small change in speed, the amplitude simply jumps along the black line, and you get a fairly large oscillation amplitude. And you can see the flow structure also changes, because the frequency has changed from the natural, the vortex shedding frequency for a stationary cylinder, as is shown in this U star 4.5, to suddenly a frequency which is the natural frequency, which may be a little bit larger. Now the vortices are released a little bit more quicker, so they squeeze together, they coalesce in the far downstream. And in fact, you can see there is some low frequency, again, splitting going on here. Okay, so that's the secondary wake, but we don't get into that today. And so the flow structure is already a little bit different. So it is still the 2S mode of shedding. 2 single vortices are released during every cycle of shedding, but the frequency is different, and that leads to some differences in the wake structures. And then the amplitude decreases, and this is called the lower branch. And amazingly, again, before it goes to the desynchronization, the amplitude again starts increasing. Okay, and then after you get this desynchronization. So it's very interesting. So desynchronization on 2 sides, which is the unlocking, and then initial branch again on the 2 sides. And in between sits the king of lock-in, which is the lower branch, which is a fairly high amplitude motion. And then, of course, because of these jumps, because it's a nonlinear system, you get hysteresis. So in some sense, what it means is if I had a tornado and I had a system sitting, at some location, so when the tornado builds up, I follow the black line. And when the tornado is receding, that means the flow speed is reducing, then actually the misery continues for till up to a smaller flow speed. So that's the hysteresis. Okay, so the information to glean from this is that at this mass ratio, that means the cylinder is 10 times heavier than the fluid. So we are talking something like maybe aluminum in water, okay, which is so 13.6 is the density of aluminum compared to water. So this is the kind of at a low Reynolds number, the response you would see. So same as the last picture. But here now I am showing you the frequency. So the frequency locks into the natural frequency, and on either side of it you see again a jump where it has gone to the stationary frequency of the system, the vortex shedding. Okay, now what happens at different M stars? That's again a very important question, and this was investigated. So here is M star equal to 70. That means if you take the same cylinder made of aluminum, but doing the experiments in air now compared to water, as small a change as that, and things change. And I'll just highlight for you what happens. So the red line is the one that we have already seen. Okay, that's something very similar. Okay, but in between, it turns out you could get multiple solutions. So if you have M star 70, then in between this lock-in branch, you could get a regime where you could have either a high amplitude vibration or a low amplitude vibration. And it really depends on how the system is put into motion. So initial condition becomes very important. If you start from a steady state solution for flow past the cylinder, then you get low amplitude oscillations. But if you are increasing or decreasing the flow speed, then the initial condition is already high amplitude solutions, and you seem to stay on that. So this is a new branch that was found, again, only for a single degree of freedom system. So if you had a larger M star, it turns out the response of the system is very interesting. You get desynchronization, you get initial branch, then this is called the lower branch where you have high amplitude. In principle, you could get another, this initial branch, and then followed by another low amplitude branch, and then of course the desynchronization. So very, very interesting. And this picture here shows in more detail what happens as you keep increasing the M star, let's say from 30 onwards to 150. And you can see this regime in between, which is marked in the grayish blue color. It becomes a little bit more rich as you increase the mass ratio. And what you would find interesting is that the range of lock-in, it doesn't change as much. So one would have expected that a heavier body compared to the surrounding fluid would vibrate for a smaller range of U star. But no, that's not what happens. It's just that as you increase the mass ratio, so heavier systems seems to be more complicated. And the lighter systems are, for example, at M star 10, you just get these two hysteresis at the onset and the end of synchronization. And in between, it is plain vanilla lock-in. But as you go to 150, you can see there's really a lot of interesting stuff going on. So this was a lesson learned, that although low M star systems would have appeal of their own, but higher M star, for example, aircrafts in air, their flow-induced vibrations would be far more complicated than in a laboratory experiment done with some body in water where the density ratio is small. So one has to be wary of that. And this is still low Reynolds number. What happens at high Reynolds number and the effect of M star? I think that's really an open question even today. Even for these very small systems where you have only 1 degree of freedom. And then if you add more degrees of freedom, of course, it's anybody's guess. So just to show you what happens to the width of the regime with multiple solution, it seems to increase linearly with M star. But of course, it cannot go on forever. So at some point, of course, it would saturate. But we have not been able to pursue that. Maybe somebody should. Can you get collapsed curves for the response? And it turns out yes. So what is shown here is data plotted in some non-dimensional variables, where I don't want to bore you. There's a reference given if you are interested. But it turns out if you take all this data from different M star and plot it in with some jugglery of variables, you could get some kind of a unified picture which shows you how the system behaves. So there is some organization to this madness in terms of M star. Okay, so very quickly, because I want to show you some other interesting stuff. What happens at high Reynolds number? So these are some pictures I have taken from Khalak and Williamson. So the left one is at low Reynolds number, and the right is at high Reynolds number, which are usually by experiments. So one big difference is the amplitude. So you get an additional branch for high Reynolds number, where the amplitude of oscillation could be larger. And other than that, there are some other differences, but I think that would suffice for us to say at this point. So we did some calculations for Reynolds number, which are not really high, as small as 1000, and the span is only 4 times the diameter. And let's see what happens to this compared to a laminar regime. So of course we would need now a parallel cluster for this. So this is a very old image, 2009. So we parallelize the code. On the x-axis is the number of processors, y-axis is the speed up. So if you had a perfect linearly speed up, you would get the straight line. That means on 64 processors, the code would run 65 times faster. But in fact, the interesting thing is if you do a good job, then you can utilize the cache effects and you can get a nonlinear or a superlinear speed up. Okay. So the code speeds up quite well. Okay, so with that tool in hand, now we can do fairly complicated flows, even though the Reynolds number is only 1000. So if you notice, axis is the same, the amplitude on the y-axis, non-dimensional amplitude, and the reduced speed on the x-axis. So you see these various branches. So there's an initial branch, which I marked with B1. B3 is the lower branch. And then B2 is the upper branch. Okay. And something very interesting happens. You get, because of this jumpy behavior, you get a hysteresis on part of the branch and then an intermittency on the other part. So what intermittency means is that at these values of U star, where this region I is marked, in fact, it is also marked in the close-up view, the state of the flow is such that you would get a high amplitude oscillation for some time, followed by a low amplitude oscillation, and there's intermittency between these two states. And in fact, it also shows up in the mode of vortex shading. So for example, U star 4.55, which you are somewhere here, you get a 2S mode of shading. But if you go to this branch, for example, 6.2, somewhere here, then you get the 2P mode of shading. So two pairs of vortices are released, one from the upper and the lower surface. So during this intermittency, the flow keeps on changing between these two states, the 2S and the 2P states, and so on. So there's very interesting dynamics here. So we did some more calculations where the Reynolds number is also allowed to change with U star. So it is shown here on the x-axis, the lower axis is the reduced speed, The upper one is the Reynolds number. And then you get things which are very, very similar to experiments. So you get a desynchronization regime, an initial branch, then a toggle between the upper branch and lower branch, then a lower branch on its own right, followed by a desynchronization. So I'm not going through the exact dynamics, but you are welcome to refer to this paper, or if you have any questions, we can discuss them later. Okay, so what happens to the flow? So if you plot the amplitude on the y-axis and some kind of a frequency on the x-axis, then there's this chart which was given by Williamson and Roshko, which kind of they did some forced oscillation experiments, and they could say that depending on the frequency of vibration and the amplitude of oscillation, you could get these different vortex shedding modes. Okay, so C, 2S, 2P0, 2P. So 2P0 and 2P are very similar. In one case, the one of the pairs of vortices is much weaker than the other pair. Otherwise, they are very similar. So our calculations also show that it matches quite well with their experiments that they have done. Okay, very quickly, I want to show you what happens if you have two cylinders instead of just one. So we did two studies for this, a tandem where they are in line with each other, and a staggered where they are not just in line, but there's also a little bit of staggering. The Reynolds number was kept at 100, mass ratio is 10, and no structural damping. And the upstream cylinder, being the first one to be hit by the flow, it kind of behaves very similar to an isolated cylinder. In fact, kindly pay attention to the amplitude. It is very similar to that for a isolated cylinder. So there is no major difference between the upstream cylinder and one single cylinder. But let's look at the downstream one. The downstream one is extremely interesting. In fact, you get this wake-induced flutter where you will see that the amplitude oscillation can be very large, more than a diameter. And shown here are different kinds of hysteresis. And there is this region between U star 6.5 and around about 9 where you could get large amplitude oscillations. So please recall the ferry bridge disaster that I referred to, where the wake plays a major role. And this is, just Reynolds number 100. So what to speak about higher Reynolds number, they could be extremely devastating. So we tried to understand the flow in terms of the phase between the oscillations of the upstream and the downstream cylinder. So Y1 is the time history for the upstream cylinder, Y2 is for the downstream, and then the phase between them. It can go all the way from minus 180 to 180. So that's the red dots. Okay, so they show a pattern. And then, of course, there is this amplitude of vibration. The reddish line, the orangish line is for the upstream cylinder, and the blue line is for the downstream cylinder. So we divided this into 5 regimes. I don't have time to go through the different regimes, but it suffices to say that they're extremely interesting. I mean, you could, for example, at U star 12 or U star 8, you can see a qualitatively difference in the response, and likewise you see in the flow. So some of the flow pictures are shown at different U star, and it's an extremely rich flow. Again, I will not go into the details, but compared to if these were not vibrating, if they were just stationary, you would see something like U star equal to 2, because there the amplitude of vibration is extremely small. Maybe I should go back to this picture. So at U star 2, you will see the amplitude of vibration is extremely small. So if you have to read the amplitude, kindly refer to the axis on the right. That's Ymax. And you can see that it's very, very close to 0. Okay, so that's what the stationary flow would look like. But once it starts vibrating, the two of them, I mean, you can see hell has broken loose. Okay, you see all kinds of flow structures. Very, very interesting. And again, what would happen at larger Reynolds number is quite exciting. Um, I don't think there has been too much work done on it for larger Reynolds number. That would be one very exciting area. Okay, so I quickly move on because I don't want to hold you for very long. So can we control these vortex-induced vibrations? So sometimes they can be useful if you want to harvest energy, but at other times they could be disastrous. So if I have offshore structures or even onshore structures, then these vibrations could give rise to fatigue. So imagine, there are cables, even electricity cables. They just keep vibrating all the time, and eventually they will fail. So the question is, can we do something to get rid of the vibrations or at least reduce their amplitude? So one idea is, can we use a splitter plate? So if we add a splitter plate to a circular cylinder, then it is known that it can weaken the vortex shedding. And the question is, what about vortex-induced vibration? Because now the plate will also vibrate. So can that be used to suppress the vibration? And we also want to study the effect of flexibility of this plate, as I will show you. So what we have done is, can the flexibility of the plate be used as a design parameter? So we did a number of simulations, okay, with a rigid plate, with a flexible plate. We looked at effect of damping, the length of the plate, mass ratio. Of course, there are still more parameters if one wants to study, but just to show you, it's a very rich area. Okay, so here is a picture of flow past a cylinder with and without plate. And you can clearly see for this Reynolds number, 150, and for this length of the plate, the vortex shading is kind of weakened quite a bit. Okay, if you took a larger plate, it is conceivable that you should be able to suppress the vortex shading completely. Okay. So the question we are asking is, if you subjected these two systems to vibrations, or they were allowed to vibrate, would there be a difference? Okay, that's the question. So here is what was done, flow-induced vibration with the plate. So the red line is the isolated cylinder. So that's the amplitude. And shown in the lower picture is the frequency ratio, F star. So we have seen this picture below, this red one. We've seen it earlier. So you see a region of lock-in, and on either side there is desynchronization. Okay, so at higher U star you are safe. Now when you put a rigid plate, then clearly the vortex shading is weaker, and therefore you get a smaller amplitude of vibration. So you can start clapping, splitter plate helps, there is less vibration. And in fact, something very interesting happens. Even though there could be vortex shedding if the splitter plate and cylinder were stationary, but if you allow them to move on an elastic support, then by choice they become steady. Okay, so this is a very, very important phenomenon. But then, the devil strikes. So vortex-induced vibration you have taken care of, but now the system starts galloping. So it's a very low amplitude oscillation. You can see the amplitude is very small. There's hardly any vortex shedding, but just the system, because the angle of attack is changing as it heaves, so that itself gives rise to an instability. So the bad news is that even though you've been able to get rid of vortex-induced vibration at small speeds, but if you have a breeze at larger speeds, then your system will go into galloping. And in fact, you will see amplitude ratios which would be much, much larger than without the plate. So in fact, you would not want to use a rigid splitter plate for suppressing vortex shedding, unless, of course, there was a way to disengage it at some speed. So you could think of a system where if the incoming flow speed is small, you use a splitter plate, but as soon as the speed is large, then you disengage the splitter plate and allow only the cylinder to vibrate, and that at such large speeds it would not vibrate anyway. But constructing such a system would be a challenge, And to the best of my knowledge, that has not been possible. So Brazilians have been they've done a lot of research because of their oil industry in this area. Okay, so this is just the summary of what I said, that VIV response is weaker, but the structure begins to gallop. And does M star affect the response? So is it sensitive to M star? So just out of curiosity, we did a number of calculations. So M star varying, excuse me, all the way from 2 to 1000, and it turns out yes. I mean, there's a little bit of difference, but at least the galloping behavior is seen pretty much at all M star. So there is no free lunch. So I will skip this and I will move on. Okay, so again we did some collapse of these response in terms of non-dimensional numbers, but I will not bore you with that. We also did what is the effect of plate length, and that doesn't help too much either. I mean, irrespective of the plate length, the galloping kind of shifts around a little bit. There is some qualitative difference in the amplitude, but really not much of a solace there from effect of length. Okay, so clearly this is not an effective strategy because you are getting galloping, and we don't want that. So can we use flexibility of the plate to dampen out some vibrations? Okay, so here now this is real fluid structure interaction, where you would be solving the fluid flow coupled with maybe some kind of a beam model. Okay. So there are now more parameters. It's not just a single degree of freedom system. There are infinite degrees of freedom. So we'll talk about the reduced velocity now, but there are now many natural frequencies, infinite number of them. But we'll define the reduced velocity based on the first natural frequency. Okay. Then mass ratio is same as before. Basically the mass of the system non-dimensionalized with some kind of a fluid that it displaces. The Reynolds number, now we'll have two U stars. So there is one U star or a reduced speed based on the spring, and there's another one based on the flexibility of the plate, and both of these are important. So we have chosen for the plate the first natural frequency, and spring, of course, there's only one spring, so that's easy. Okay, so before that, we tried to do this benchmark problem for the Turek and Ron, and you can see there's a fairly good agreement between the data from them and what we computed. So there was some reliability of the code that was established. And we also tested our mesh moving scheme. So now the challenge is that on the fly, you have to solve the fluid and structures, so they feed into each other. And then the mesh also distorts along with the geometry. So we are not using a the lattice Boltzmann kind of method or immersed boundary methods. This is actually a mesh that follows the body. So here, this monkey on your back really disturbs you, how to generate a mesh with these large deformations, and it should not break down. So there are sometimes this motion can become so large and so complex that mesh generation would be the driving constraint in running these simulations. Okay, so some benchmark problems were done. So this is from Wall and Ram, a little bit higher Reynolds number, 330. And this is our present calculation, and there are some other results that people have presented. So we are quite happy with the comparison, so we went ahead. Okay, so first, what about the natural frequency? So just to get the terminology in place, the reduced speed defined on the basis of the first natural frequency of the plate, so that's UP star. So as UP star increases, that means the plate is becoming more flexible. Okay, and F is the natural frequency. So this is the first mode, the red line, and you can see the first mode of vibration. There's the second mode, third mode, fourth mode, and so on. Okay, and these are the non-dimensional frequencies from the Euler-Bernoulli beam theory. Okay, so we did this Reynolds number 150, M star 10, and shown here are these three pictures, three videos. So a very low UP star, and you can see the plate is vibrating in the first mode, and there is this regular 2s shading. And then something like 37.9, which is somewhere here. And you can see now it's not really the first mode, it's a mix of second and third mode. And then at 100, it's even more complicated. Okay, and you can see that the not just the vibration of the plate, but the fluid behavior is also quite different, and certainly very different than what you would see for a stationary non-vibrating plate. Okay. Now, if you look at the amplitude of vibration, the response of the plate, that's quite interesting. So you get first a resonance with the first mode. So the red line is the first mode, and you get a resonance with that. So you get a small amplitude vibration. The close-up view is shown here. And then it becomes quiet for a while, very, very small amplitude vibration. And then you start getting lock-in with the second mode. Okay, and that's what is shown here. The frequency, the natural frequency is in the blue line, and of course the frequency of vibration is in the red line with the square symbols. But the amplitude you can see has grown and got saturated. And if you go further, you would now get a lock-in with the third mode, then with the fourth mode, and so on. So now you have a situation where for a multiple degree of freedom, you would start getting lock-in with different modes of vibration, different natural modes. And in fact, that's what is shown here. The M star shown here is 5. Okay, and these are now different modes: mode 1, mode 2, mode 3, and the response is shown in the red line, the frequency, and then the amplitude. So the lower picture is the amplitude, the upper picture is the frequency. And you can see the first mode clearly, the frequency is close to the first mode, then the second mode, and then with the third mode, and the flow changes accordingly. So I will not have time to go into the details of the flow, but Furkan has written this up, and if you are interested, you can read that paper, and he's explained that quite well actually. So it turns out that this system also has very interesting features in terms of hysteresis, and one of the hysteresis is shown here. Okay, so in the frequency domain, it looks very intuitive, but if you look at the hysteresis diagram in the amplitude domain, the response domain, it looks a little bit non-intuitive, at least to me. Okay, but in the frequency domain, it looks very, very intuitive. So I thought this was very interesting. Of course, it can be explained why it does this. So here is a complicated picture, which I apologize, it's a little bit busy, but because of my laziness, I did not make it simpler for you. But I'll just tell you what is important. So Reynolds number is 150, and part of the data you've already seen, and there's some more data here for M star. So 1, 2, and 20. So there are 3 M stars that are being done. Okay, and they are written over here. So M star equal to 1 is with this reddish color, M star 2 is with the bluish color, and M star 20 is with the green color. So you can see the amplitudes, how they change with M star. And you can see the regions of the lock-in, that also changes, the hysteresis also changes, the frequency response also changes. And in fact, at some points, what you see is this is the average displacement of the tip of the beam. So at some U stars, the beam does not vibrate about the mean position. It kind of has a bias, and therefore the average tip amplitude is not zero. It has a finite amplitude. So this is again very interesting. Um, and then Furkan was also able to figure out what is the uh, mode that contributes to the energy of the vibration. So for example, this red one is m star equal to 1, and at this u star, you can see primarily the pie chart has a purple color in it. So it is primarily the first mode. Whereas at another u star, it is primarily the second mode. And then you could have a situation where you could have a third mode which is playing a role. So we tried to figure out which mode is playing a role, and that's what we have marked here. Lock in with the first mode, lock in with the second mode, L2, L3 is lock in with the third mode, and L4 lock in with the fourth mode, and so on. So very, very rich dynamics. How do you unify all this? So all this data was taken from all the simulations, different mass ratios, and we again put it on the Williamson-Roscoe plot, okay, which they have done for a circular cylinder. So just a cylinder without splitter plate, and what are the different kinds of vortex shedding modes you get. So we took that figure and zoomed in towards our range of parameters. So for example, what is shown here is 0.5 to 3 from this image. And the y-axis is the amplitude, the RMS of the tip of the filament. And very beautifully, they actually fall in place. So for this regime, you get the 2s mode of shedding. Then you get 2p, where two pairs of vortices, you can see in this picture C1, where you get two pairs of vortices shed in each cycle of motion of this plate. You could get 2p plus 2s, where two pairs and a single each, they are shed, and so on. So it's a very, very rich dynamics, and Furkan has very painstakingly tried to put it on this picture and shown that even though the flow is so complex, but it actually behaves very similar to as if there is no splitter plate, just like an isolated cylinder, which makes sense because these vortex shedding patterns are really the result of a wake instability. And the wake instability should not really depend on the body. It depends on the profiles of the velocity field in the wake, and how they are generated should not be so important. So in a sense, the simple result makes is consistent with what we already know. So no surprise here. Then Furkan went ahead and tried to figure out if you want to do energy harvesting. Then he tried to figure out what is the energy transfer per unit time. He called it as P. So this is a picture of P from min to max. So negative means you are putting into the system, positive means you are draining it out of the system. And then he tried to figure with time and space. So time is the y-axis, x is along the splitter plate. How can you, which is the main part of this filament from which you could, if you posted some kind of a energy sucking device, where should you place it so that you can harvest energy? Okay, he has also done supercritical cases, for different mass ratios, that if the system was not showing vortex shedding to begin with, the stationary system, but then you put an elastic plate, does it give vortex shedding? And the answer is it does. And in fact, the system can go into flutter and so on. But I don't have time for that, so I'll kind of skip it. And maybe what I'll do is I will just show you some pictures of, one example is this symmetry breaking case where the mean amplitude is not zero. Okay, so there's a bias. Okay, I'll quickly skip this. I don't think I have time for this. Maybe I'll just say a word about this one. So on the x-axis is the reduced speed based on the spring. On the y-axis is the reduced speed based on the plate. And one can actually mark on it that in this parameter range, what is the amplitude of the vibration of the cylinder. And you can color code it. So blue means it's a very quiet system. Red means it's a very loud system. It's vibrating a lot. And you can then identify when you design your splitter plates and the spring stiffness that which combination of U star and UP star would you like to use, so that either you can get low amplitude for vibration suppression, or if you want to do energy harvesting, maybe you should get large vibrations. So you can use that as a design philosophy. How about two cylinders with filaments? So here is a small summary of what was done. So there are three reduced speeds given here: 3, 4, 9, 16.5, and these are filaments just attached to cylinders, tandem cylinders. Sorry, not tandem. Just next to each other. And what is important here is the amplitude of vibration of the upper and lower filament. So let's take a while to look at it. So the lower filament is so they mostly have similar amplitudes, but you can see there is small difference at larger U star. So there are these different regions of lock-in, and shown in red line is if you have a single cylinder with a filament versus two cylinders with a filament each. So qualitatively they are similar, at least at low U star, but at larger U star they are different. And you can see these very interesting flow patterns. There's also a bias now which comes in as expected, because these filaments will kind of allow the flow to go in between, and they will have some average deformation. So we tried to figure out the POD modes of the filaments, the energy carrying modes, and that analysis was done. Rather, I will show you, instead of circular cylinders, maybe some work that we did a while ago on two square cylinders with splitter plates, and something interesting was found here. So if you look at this animation, what happens that initially these plates, when the flow is started, they actually vibrate out of phase. So the upper plate, when it goes outwards, the lower plate also goes outwards. Okay, so it's almost like clapping. They're out of phase. But then after some time, maybe time units of 200, they start vibrating in phase, almost like synchronized swimming. So there is a change in phase that you get with time. Okay, the upper picture shows x-axis is the U star and the y-axis is the amplitude. And you would see if we concentrate on the blue dots, that's the amplitude, that at some UP star you get desynchronization, and then boom, you get large amplitude oscillations, which is shown here. Okay, and you see similar things for the frequency. So these are frequency which are kind of different from the natural frequency, and then here they kind of lock in with the system, and that's why you get large amplitude vibration. So I have very little time. In fact, I am out of time, so I will skip all this, and maybe I will just show you some animations. I will skip all this. So in the initial days when Furkan was setting up his filament code, this membrane code, we tried to do balloons. So we made a 2D model of a balloon just to test the mesh moving scheme, and if we can inflate this membrane. So this is a balloon with a very large modulus of elasticity, and then you get these oblate things in the horizontal direction. Little bit spherical, but now if you reduce the elasticity, then of course you get these longish balloons as expected. Okay, Then he, of course, moved on to 3D balloons, and he wanted to model bursting. So I will very quickly just show you the animations, and I will stop. So these are actually, he was able to inflate a balloon by using appropriate boundary conditions. And it turns out that these balloons, when they inflate, you already get some kind of this jerky motion. So you get a little bit of vibration when they inflate. And then he tried deflating them, and the same thing. So they don't just deflate, without any natural vibration. There's a built-in vibration that he sees. These are some toroidal vortices. And the interesting part is he tried to, so he had to modify his algorithms and so on. But I would like to show you some bursting simulations that he did, where he inflates a balloon and puts in a disturbance, and then these balloons can fail. Okay. So you can see the traveling waves, and then he can simulate how these balloons, they fail. It's a very primitive model, but nonetheless a little bit exciting.